Hi, my name is Haozheng Li, and today we are going to talk about the quicksort algorithm. The quicksort algorithm was developed by British computer scientist Tony Hoare. It is pretty efficient and general purpose. It uses the idea of divide and conquer. It is also known as partition exchange sort. We will soon see why, but before we get started, here is a quick question. What exactly are we doing when we sort? For instance, here are two arrays. The first one, we can easily say that it is unsorted. The second one is sorted. But why? Why can't we say that? Here is a way to think about it. When we are sorting an array, what we exactly are doing is placing each element in the array at the appropriate position, which brings us another question. What exactly does the word appropriate mean? Well, it means that items to the left are smaller and items to the right are larger. For instance, the reason why we place the element 3 at the third of the array is because that there are two elements, 1 and 2, which are smaller than 3. That brings us the definition of pivot. Pivot means that the element is in the correct position in final sorted array, and the items to the left are smaller, items to the right are larger. Here is an example. If we choose the element 3 as the pivot, we will get this array. And notice that there are two elements, 1 and 2, which are smaller than 3, so we place them in the left and the others in the right. We should also notice that it gives us two sublists which are unsorted. That brings us the idea that maybe we can solve this problem by the sort of recursion. And that is the idea of quicksort. We can focus on this pseudocode. First, we make the index of the pivot by the return value of the partition function, and then we recursively call the quicksort function. The first call of the quicksort starts at the beginning and ends with the pivot index -1. The second one starts at the pivot index +1 and ends at the end. We should also take a look at the pseudocode of the partition function. First, we make the end of the array as the pivot and initialize I as beginning -1. The main idea of this for loop is finding every element which is smaller than the pivot and put them in the left. And finally, we swap AI with AN in order to put the pivot in the right position. It is pretty hard to just looking at the pseudocode and get the idea, so we will follow an example. Notice that this example is the very first call of the partition function, so the beginning should equal to 0 and the end should equal to 8. Since the pivot is the end of the array, so the pivot now is 3, and we initialize I with -1. Now we are in this for loop. The j should initialize with 0, so aj now is 9. Is 9 less than or equal to pivot, which is 3? No, because so we need to continue. Is 8 less than or equal to 3? Still no, so we continue. And the same idea with 4. Notice that 2 is less than 3. So we need to execute the code here. First, we add 1 to I, which means I now is equal to 0. And swap AI with AJ, which means we swap 9 and 2. After that, we continue the for loop. Now j is equal to 4. Is 1 less than or equal to 3? Yes, so we need to execute here again. I is equal to I plus 1, which means AI is 8. Swap AI with AJ, which means swap 8 and 1. After that, we continue the for loop. Notice that 5, 6, and 7 are all larger than 3, so we reach the end of the for loop. Then we add 1 to I, which means AI is equal to 4, and swap AI with AN. Now 3 is in the right position. After that, we recursively sort the whole array. Here is the animation. After the recursive call, we will get the final sorted array. At the end of the discussion, we need to analyze the time complexity of the quicksort algorithm. First, we focus on the best case analysis. The best case of the quicksort is each time we divide the list into 2 equal sublists, which means if we consider the time complexity of the quicksort as Tn, Tn should equal to 2 times T, n half of the n plus On. Here, On means the time complexity of the partition function. By using the master theorem, we can easily get that Tn should equal to O n log n. Now we take a look at the worst case analysis. The worst case of the quicksort is only get the sublist of size n minus 1, which means Tn should equal to Tn minus 1 plus On. And by unwinding this formula, we should get that Tn is equal to On squared. On average, the time complexity of the quicksort is On log n. Thank you so much for watching, and see you next time.